All right, are there any that we should talk through?
Just, I want to make sure I got the right answer on 10. Number 10?
Yeah. That was a little
Zilla
Oh,
10?
there's 10. It's on the next page.
Did you not flip the page?
I didn't flip the page.
I don't know if you've caught on yet, but there are always 10 questions at the end of the book. Okay, well, you get a little grace here. A young boy found a large box that he can use to make a fort. Yes, I like this kid already. He put some other treasures he found into the box, so it weighs 11 pounds. Tied it to the back of his bicycle and is pulling it down the road. What force must he pull the box with in order to keep it moving at constant velocity? Okay, so, Daniel,
Sure.
why don't you just come up here? Actually, you can do it. I'll let you do that down there. Wilson, draw the problem up for us.
Oh, joy.
Yes.
I-
It's joyful.
What has the? I'm.
The book is right here.
Drawing.
What should Wilson start with?
The box.
Finding the
Do I
moves.
have to draw the box in 3D?
I don't know if you need 3D for this, but
I have it in 3D.
I like the idea of drawing.
It's 11 pounds.
Yep, 11 pounds.
And then you got dot 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 dot, and that's the chain. And person. Bicycle. This is not good at all.
That's okay. That part doesn't have to be too crazy.
And we're looking for this. I believe that not an acceleration in pounds. Yeah. And then
So, what's in the box weigh? The whole box weighs 11 pounds, right?
yes.
Okay. And he's dragging it, right? Okay. How do we determine how much force it takes for him to drag that box?
What are you doing? I mean, the
So
chain
the box is already moving, and the question is, what is the force that he has to pull to keep it moving?
To keep it moving, right?
At a constant rate, so that means that acceleration has to be 0, correct?
Yeah, what force does he need to keep
Yeah,
it
it
moving?
says
So
he's
there's no
already-
acceleration at this point.
moving at a constant velocity, so sorry.
It's just how much force does it take for him to keep it moving?
Well, if you multiply the kinetic friction coefficient by the normal force, which is 11 pounds, and you get 3.52. What is it?
So,
Meter.
I'm gonna write the thing out.
Yeah,
The friction.
the F sub FR, right? A force of friction would be equal to
3.5.
What's M? That's something.
now. What are you putting up there right now?
I'm putting the friction forces.
Gotcha. And how do you know which one you need?
It's already moving, so kinetic is when it's already moving.
Very good.
Static is when you're trying to get it to move.
Okay.
So multiply 11 by, I guess I should do an X. 11 by 0.32, which was what, 80? I guess I could just look at my own page.
Yeah, no cheating, man.
Hey, stop cheating.
I mean, he said it out loud. So this is pounds.
Yeah, good. It's pretty much that simple.
Yep. And then the way that we would figure it, or I guess the way that you would figure out if there was acceleration, wouldn't you? Or I guess if you're trying to find acceleration, you would do the whole thing where you subtract the force minus the friction. Well, because like.
Yeah, but they didn't give us a force is the
Yeah.
problem, right? So they could give us a force and we could calculate an acceleration, or they could tell us this is accelerating, and then we could calculate a force that was a net force, kind of like we did on last week, right? Or we could, what else could they do? They could tell us, they could ask us, what coefficient of friction do we need to be able to accelerate this thing, right, with a given pull force? We need to be able to accelerate it this fast. How good of a surface do we need underneath this? That could be another way that you come at a problem. Just based on the fact that sometimes as an engineer, you're picking materials to do what you need, right? It's not so much that it's like, well, this is the situation I'm in. It's like, what material do I have to specify in order to make my thing work, right? I'm building a machine. My machine has thing A sliding against surface B, and I've realized I'm not going to have a powerful enough motor unless I have a good surface here, because my motor, let's say it's my motor right here pulling on a line, and I've only got space for a 1/2 horsepower motor, let's say, and at this diameter and so forth, maybe that's 6 pounds of force, and I'm going to need to, in order to get this thing to move at a certain rate, I'm going to need to keep my friction really low here. So maybe I'm going to put micarta or UHMW, which is like a high density slippery plastic, something like that, in between my two surfaces, so that I can drop that friction coefficient down and not waste energy. Because otherwise I have to oversize my motor and my machine gets more expensive and I can't beat my competitors because I didn't put in a $2 piece of plastic. Okay. Okay, so here's what we're doing for Chapter 5. Chapter 5 and 6 are closely linked in that the concepts that we introduced in Chapter 5 were what, primarily?
Laws.
Yeah, Newton's 3 laws, which are what? Just go to my back pocket.
Inertia
First one, inertia, meaning,
means if a object is motion, it will stay in motion.
Okay, good. Joseph, second one?
Force equals mass times acceleration.
Okay. And?
Action and reaction is the third one.
Opposite and equal reactions. Good. Okay. So we concentrated somewhat on F is equal to ma. The principles of the first and the third apply, right? Give us insight. But F is equal to ma just keeps coming up over and over. And guess what we're going to do in Module 6?
More.
All F equals ma. Yeah. So I'm going to start teaching into Module 6 today, and you guys are going to do this test for Module 5 as a take-home test. So I would say I just want you guys to work through that, and I don't think you need your books for it, honestly. If there's something that's like I don't know, what is the acceleration of gravity on the moon? He's not going to require that kind of stuff from you without a book. But if there was something like that, I don't care if you go look it up. But that is the homework for Wednesday. Okay?
Wednesday?
Did I say Wednesday?
You said Wednesday.
Friday. That is the homework for Friday. Today is Wednesday.
I was gonna say.
I want it done now! Okay. So, when we start thinking about Module 6, he introduces a few concepts. I'm going to run through those so that verbiage makes sense. If you want to follow along in your book, it's page 177. And the first thing he introduces is this idea of translational equilibrium, which is a very fancy way of saying, what does the word equilibrium typically mean?
Balance between two.
Yeah, balance, right? Equal. You can see that in the prefix of that word, equilibrium. So an object is said to be in translational equilibrium when the sum of the forces acting on it is 0. So, Wilson, is this in translational equilibrium? This pencil pouch. This lunchbox.
Yeah, how many pencils do you have there, guy?
Well, see, in my house, the lunchbox is this big and the pencil pouch is this big.
That does make sense. But
I mean,
Is it in translational equilibrium?
unless you count the little chain, then yeah, because it's like bobbing right now.
Oh my gosh. Killing me, Smalls!
I love
Yeah.
that. It's
Okay,
freaking love that.
so, yes, that's in translational equilibrium. What if I throw the marker to Joseph? Is that translational
That is an
equilibrium?
open mark.
Not until he's caught it, except for not now, because he's not doing it.
Okay, right, while it's in flight,
If it is stationary, it is in equilibrium. If it is
what if it's just rolling along,
it's rolling, then it's not.
but it's not accelerating?
But that means that there's if it's weird.
Let me ask you a question. If a spaceship is moving through space, its booster rocket is gone, and it's going 1,000 meters per second, is it in translational equilibrium?
I mean, I guess nothing else is really acting on it. I mean, since the acceleration.
Yeah, exactly. Yeah, ask yourself, what forces are acting on it? None. So it is in translational equilibrium.
So it doesn't just have to be sitting.
Okay, so now we say, then we
So then
split this idea of translational equilibrium into two things, right? We split them into the two situations we were just talking about. Static equilibrium, which one do you suppose is static equilibrium?
When it's not moving.
Yeah, it's the lunchbox. And into dynamic, which obviously is the spaceship, right? Flying through space, but not having any of its burners on it. Does that make sense? Okay, so we're just running through these definitions and terms. The reason it's important is one of the first things we do is when we're analyzing a situation is we're looking at where the forces are going, what forces are acting on an object, right? And we have to break those down in a way that allows us to then solve whatever the problem or question is. So the book gives the rather trivial example of a lamp hanging down from the ceiling. So let's think about the lamp. Is it in dynamic equilibrium or static equilibrium?
Static.
Yeah, it's in static. And let's draw the forces on it. What forces are on the lamp?
Gravity.
Yeah, so from center of mass, draw an arrow down, and gravity we know is equal to what? Well, that's the gravity on Earth, but gravity in more general terms, the force on this is the mass times whatever the gravity happens to be, right?
Oh, yeah,
MG.
we're talking about weight.
Yeah. Yeah, that's the force pulling down on this thing. What's preventing this thing from falling to the floor?
The tension of the rope.
The tension on the rope. And because of Newton's third law, what do we know about the tension in the rope?
That it has to be equal to the weight of the object.
Yeah, it's going to be equal and opposite to that because this thing is not accelerating, right? So the forces on it, the net forces on it are zero. So we can know that the tension minus mg is equal to zero, right? We've said that the sum of the forces, and have you guys ever seen this notation before? The sum of the forces is equal to
That's a sigma right there.
the sum of the forces is equal to the tension, because that's one of the forces, minus gravity, that's the other force, right? And those have to be equal to zero because this isn't moving. So then we can just move mg over. We obviously show that the tension is equal to mg, right? Trivial, but when we start with a block on a slope or some other thing, it gets complicated when you start working this in 2 dimensions, and you have to think clearly. Okay. So that introduced us to this idea of tension. So let's do a more complicated tension problem. It's a pretty common one, actually. let's say you've got a guitar. All right, and here's the neck, here's the body. And let's say we hang, let's say we only have one string on our guitar, because we're doing an experiment with our guitar. We're not actually playing it right now. It's over here to the bridge. Okay? And that's the path that the string would follow if there was nothing hanging on it. But we've hung a 4-pound weight. Or applied a 4-pound force, right? So a pretty small number of slugs, like 0.1 slugs or something, who knows what the number is offhand, but a very small weight, 4 pounds, on that string. And it bends the string downward, right? So let's say, just for the sake of argument, that it drops ½ inch. Whoa. Okay? So you put 4 pounds onto the wire, drops ½ inch. Question is, what's the tension
With the string.
in the string?
A lot. If 4 pounds is as much as I think it is.
½ inch is a very part of
No, it's not. That's
What else do we need to know? We need to know the distance between these 2 points. Do you see that? We need to know how long our string is.
Oh, what kind of guitar is it?
Oh, typical guitar string about 3 feet.
Well, I mean, it depends on the length of the neck and the.
Well, I know it depends on that.
style.
About
the style of this.
3 feet, right? We're gonna say that this is 40 inches. Just gonna keep our numbers simple. Okay, it's 40 inches long. Bass guitar. That's 36, that's not 40. That's a little bit long, but it's not too bad because it's like a bass. Let's knock it. Daniel.
technical.
Squirrel. Okay. So if this is 40 inches across, and this is dropped ½ inch, okay, we can draw a little picture here, right? That just kind of moves us away from the guitar into something simpler, right? Yeah. 4 pounds. And let's look at this area right here and think about the forces acting on that spot. We've drawn the 4 pounds, so we know that force is acting. What else is acting as a force on this point, on this little mass that we've put on the string?
Tension from the wires, but it is straight up, but it's divided into 2 vectors,
Well,
right?
yes.
Well, let's start with thinking about, can you make a rope apply a force in any direction other than the direction the rope is traveling? No, you can't, because it's a tension-only element, right? If you put a rope into compression, doesn't work. If you put a rope into bending, no resistance, right? That's what's so great about ropes, right? So we know the force on this point has to be that way and that way. Do you see that? The other thing I didn't tell us, but I probably should have, because it would matter, is that we put the weight right in the middle. So this is 20 inches, right? So now we know that we have, what do we call a force like this with a direction associated with it?
A vector,
Bingo, it's a vector.
boy.
So now let's think about how these vectors divide up. This one is just vertical, like it's right in our y direction, right? That works reasonably well for us. These don't work so well for us. They're hard to combine with this, and they're hard to combine with each other. You see that? So what do we do with them?
Split them up.
Yeah, we're gonna find their components, right? So can you see graphically, there are two components to this vector. One is a tension that's pulling away. Do you see that? That direction? And the other tension is an upward tension. You see that? Okay, same thing over here, right? It would help to do these in a different color. I like that idea. Okay, and then the components on this one do the same thing. Over and up, right? What do you notice about these vectors? Can they be combined now?
Yes.
Okay. What is the combination of these two vectors?
0.
Yeah, it has to be 0, right? They're good. The tension in the rope
Because it's not moving.
is the same on both sides. It has to be. Because that rope is a continuous element, right? With a tension on it. And so you can't make the tension in this part of the rope be different from the tension in this part of the rope. Okay. So we know the tension here is the same as the tension here. And that means we know that this, since it's in the middle, right, 20 inches, we know that these angles are the same. So if the angles are the same and the hypotenuse is the same, the hypotenuse is the tension, then we know these legs are the same, and they're in opposite directions. So we know that they cancel entirely. What about these two?
They add together to make 4 pounds, right?
They would have to add together to make 4 pounds. Yep, exactly.
4 pounds.
We can call that T1Y and
What are we
T2Y.
trying to find?
We're trying to find the tension. So if the
Of
tension is
both of
just
them together or of an individual one?
We know T1Y, like you just said. T1Y plus T2Y has to be equal to 4, right? And we know that T1Y equals T2Y,
So the answer is 2.
right? So the answer is that both of these have to be equal to 2, right? Okay. So T1, so I'm just going to call it then Ty at this point is equal to 2. Now, if Ty is equal to 2, stupid lamps make a reflection on it. But I don't know a good way to fix that. Okay, anyway, I think this is a better color for visibility in general. Okay, so what do you suppose we do next if we want to find out the tension in this line?
Well, don't you have to find that angle? You're gonna try to find the hypotenuse of one of the triangles.
Good, yeah, we have one known side, right? I don't know what this is. I don't know what this is. I do know what this is. And I can find its angle because I've got the geometry, right? Do you see that?
You.
We'll give you a mulligan on that.
If you have 2 pounds of pressure in the y direction, can you use the distance in some way? Because like, yeah, you can use like 20 inches.
Yeah, we have geometry here, right? Because this draws out, think about it. This draws out a triangle that looks like this, right? And this distance is what? Yep, and this distance is what?
20 inches.
Okay. So
That is
it's
the
not
most
at all the scale.
well scaled thing I've ever seen.
But you can
Okay.
do the.
Make sure that's still recording.
One
Okay.
angle.
Okay, so what is the angle right here?
The inverse tangent of 1/2 over 20.
Tangent is equal to the opposite over the adjacent, right? TOA. So the tangent of theta, I should say, is going to be equal to the opposite, 0.5, over 20. So we're going to take the theta is equal to the inverse tangent of 0.5 over 20. Make sense? Okay. What is that number?
1.43 or one, so like 1.4, which is like, that's so small.
1.4 degrees. Okay, that's fine. That's what I reasonably expected. Okay, so 1.4 degrees is this angle right here. Can you see that?
It's also
Okay, so now let's think about our triangle in terms of the forces instead of the geometry. See, now we've solved the geometry, and that gives us a chance to do it by forces. So let's take, I'll do it more realistically this time. That will help everybody feel better, right? What goes here?
2.
2 pounds, right? And then right here we've got 1.4 degrees. What's the value that we want? Yeah, right, because this is the tension, right? That's what we're interested in. So, Daniel, which trigonometric identity is going to help us in this particular case?
Sine.
Yes, sine, because sine is going to be the opposite over the hypotenuse. So, we know that still visible, good. The sine of 1.4 degrees has to be equal to the opposite 2 over the tension, right? Now, I'm going to solve this so that I can get tension by itself not in the denominator, right? So I'm going to multiply both sides by t, and I'm going to divide both sides by sine of 1.4, right? So I get t is equal to 2 over the sine of 1.4 degrees. So what is t equal to in this case? 82 pounds.
That's a lot. Are you sure about that?
Yeah,
That's a lot. That's some crazy cupcake.
it's surprising, isn't it?
Why did we switch the thing to 2? I missed that. Why did we switch the number from 1/2 to 2 on this side?
Okay, so the 2 is 2 pounds. We're calculating
Sorry.
pressure or
This is-
tension.
This is the force, 2 pounds.
as opposed to 2 inches.
Okay, cool. I just missed that.
So here's what's interesting about this. We're ignoring one thing that's important to realize in the real world. Because if you set this up on your guitar, okay, and you put a force meter right here, would you get exactly this answer?
No, you would.
Why would you not? What's happening that is in reality a real thing that we're not accounting for?
Human error.
Errors.
I don't know what you said.
Air resistance.
It's always air resistance.
That was
we
the
neglect.
answer for so
Yeah.
long.
Friction! It's friction!
That's not friction either in this case. What are we neglecting?
Exact measurements.
No, no. Your measurements are perfect.
Yeah, the
Oh,
force.
You're
Measurements have
neglecting
never
something.
been perfect.
It's not at a point.
The material.
It's at like a.
What about the material? What material?
What's its frictional thing?
No, the friction doesn't matter.
Let me ask you a question. Would it matter whether this was the high E string or the
A string.
one of the other strings next to it?
Whoa.
Would it matter which string?
Yeah, because the strings.
Why?
They're not all the same thickness.
And so what is that changing?
It's changing the
Tension that it has.
Okay, most things in the world, virtually all of them, are springs. i.e., they resist a tension, right? And they change length when you put that tension on them. A rubber band changes length Right? to one extent. We've assumed that this is infinitely stiff, right? This is like a carbon fiber. Carbon fiber is pretty stiff. Stiffer than steel. Carbon fibers that we've put here or something, right? Because we've treated it like it's super, super stiff. And we don't know, in reality, a string that is only that tiny around, I've blown it up, right? If it's so small and you put a bunch of tension on it, well, what happens is that string stretches over that distance, and when you put a tension on it, it gets a little longer, right? And when it gets a little longer, then this can get lower, right? So with our 1/2 inch, we're neglecting the fact that our string has been stretching, so we wouldn't quite be able to get up to this 82 pounds of force. Maybe it's only 60 pounds. I don't know the number. But we could calculate it. We're not going to go through that right now because it's not what. But I want you to just realize the sorts of things that we're setting aside in order to learn basic principles here, right? But I wouldn't want you to like set this up at home and go, Cully lied to me. Son of a gun. Okay? But that's pretty interesting, right? Now, what are the implications of this for kids, little kids making forts outside in their backyard, and they want to run a line from their bedroom window in the backyard into the fort? Let me draw a picture of what I'm talking about.
I tried to do that a long time ago, and it didn't work. I fell, like, we got on the line, and then I fell out my window.
Yeah, so here you have, right, you've got his house, right, and he's got a window on the second floor, and then there's a nice tree in the backyard,
Literally, yes.
and he's got a fort up in it, right? And he says, I want to make a line that goes from my house over to my tree house, so I can go.
You have no clue how annoying it was to try to get the line from the treehouse
To the
up
house.
into my house.
Yes.
Because I had to like chuck it up and then sprint up and try to catch it before it fell
Stepped back
down.
out. Yeah.
Mm-hmm.
Okay, but
I was dumb.
based
I
on
didn't do it.
what we just learned from this problem, Daniel,
Eh.
what does this youngster need to be careful about?
The tension of the line and how much he weighs, because he's a dumb little idiot kid and he'll fall.
Okay, hang on. Let me ask you a question. You're not catching on to what I'm asking. Is it better for him to string this tight and then tie it off? Or is it better for him to leave some slack? Why?
Because you can deal with the weight better than the high tension will snap if it's
If
just
he-
a
Because
little
there's already
slack.
tension on the rope when it's pulled tight.
If he sets it tight, let's draw what would happen between his. So he sets it tight. When he gets onto it, right, it stretches like this, right? And so all the force of his body, right, has to be reacted by the little portion of the string vector that is vertical, right? If he had just given himself a little slack, I'm exaggerating obviously, if he'd given himself some slack, do you see that for the same given tension, you would have way more force, right? In the vertical direction, resisting him, because he's pulling down right here, right? And so the advantage is when you have more slack, the force on the anchor points is lower. Right? Because these anchor points, right? We just said that the guitar would have to resist 84 pounds of force. If we resisted the same 4 pounds, but the string was dropping 4 inches instead, think about how sine was 1.4 degrees. Now it's going to be 5 degrees or something. And how much smaller that force is going to be at the end. That make sense?
Yes.
He's the same weight. The line is the same. The distance between the points is the same, but the distance that you've dropped is very different, right? And that distance changes the angle, and the angle determines what component of the tension force can actually contribute to resisting the fall, right? To keeping this object that's here from going to the earth. Okay, does that make sense? It's a cool principle. All right. So that took me through page 179 and 181. He's been working through the problem there. You found the tension in the string. Okay, so Now we do a slightly different problem. It's very similar, okay? But the thing is no longer in the middle. Okay? So I've got a flower pot that I'm supporting on a line. Okay? And I've got about 40 degrees here, and I've got about 30 degrees here. And let's see here. I want to see how he approached this, because there's a couple ways we could approach this. One is the string is continuous through this, and there's a pulley here. If we did that, what would our flower pot do? Would it stay here? No. Do you see why? Because if we did that free body diagram of our flower pot, it's got unequal forces on the two sides. Because this one is flatter, right? The arrow to the right is going to be bigger. Ooh, I'm trying to make it. Because the angle here is flatter, this would be little turkey. Oh, it's still recording. Good. Okay. And so what happens when you have unequal forces on an object?
It's gonna move towards the one that has more.
Yeah, it's going to move, right? And that makes sense, right? We would see if this was on a pulley, the basket would slowly move to the middle. Can we see that? Because once we got to the middle, these would no longer be unequal, they'd be the same, and now the object doesn't want to accelerate anymore. What's that?
We would reach equilibrium.
We would reach equilibrium. That's right. Okay. So, what do you have to do in order to prevent that from happening? You have to like put a knot here or something, right? Now, once I put a knot here, does the tension in these two have to be the same?
I mean, isn't the pot gonna be? Oh, I guess no. I thought the pot was gonna be like twisted a little bit to the right, but it won't. But if you do it right.
Say that again?
I was thinking that the pot would be tilted a little bit to the right, but you have if you do it right, it wouldn't necessarily do that.
Yeah, no, the pot's just going to pull straight towards the earth from its fixed point. So, I think the answer is no, the tensions do not have to be the same in the line anymore. And you could kind of prove this to yourself by it always helps to take things to the extreme when you're thinking about a problem. You're trying to get insight. Does that make sense? So what if, it's not the problem we're doing, but what if we just took a moment and did a mind experiment and said, I tied the knot at my pot right here. So my pot's right here, line is here, and this line is here. Do you think it would be hard for the person holding this line? Are they going to hold much of the weight of the pot? The tension is going to be very small in this line, isn't it? The tension is going to be most of the weight of the pot on this end. So these don't have to be the same tension. You can kind of see that when you start thinking about it. Okay. In fact, right, because you could start the situation with the pot hung from a single point, and you tie a line to it here, but you're not pulling on it yet. And then you just slowly start pulling on it, and this thing will slowly start to swing over, right? And so the tensions obviously don't have to be the same. Okay. But if there's a pulley right here, then they have to be the same, because that line is continuous. All right, so the way he set this problem up, I'm looking at page 182, so you're welcome to follow along there. He says, first thing to do is figure out all the forces that are acting on the object of interest. What is the object of interest in our case? The flower pot. Yes. And it says gravity's pulling straight down while the tension in each string is directed along the string. So here's our flower pot, right? And gravity is pulling down on it. And there's one force going off this way at 30 degrees. to the horizontal, and there's another force going off this way at 40 degrees, right? Okay. Our final goal, he says, is to add these forces together and set them equal to 0, because the flower pot's in what kind of equilibrium?
Static.
Static, right? Because it's not moving. But the forces are not directed all in the same direction, so we have to break them down into their components. When breaking vectors down into their components, however, we must be careful how we define the angle. An angle must always be defined counterclockwise from the positive x-axis. This is indeed the way the angle is defined for T1, so its component is an easy task. To find the component of T2, we're going to redefine the angle. The angle is currently 40 degrees from the negative x-axis. In order to define it from the positive x-axis, the angle becomes 140 degrees. Remember how we did the 180 minus business? Now, this is where, if I'm doing work like this, I don't, it becomes important when you're doing big systems of equations to always define the angle relative to the same point and to carry it like that, because it gets to the point where the math is doing the work of following what the diagram would do for you to keep you straight, right? You can draw a diagram, which is what I typically end up defaulting to at this stage of my life, and making sure that I understand which way stuff is going. But if you strictly follow what he does here, you'll get the right answer, and it scales to big complex problems well. Does that make sense when I say that? So we'll follow it the way he's doing it. So first of all, what is, we're going to call this, I want to make sure he called this T1, he called this T2, okay? So T1x, right, that's going to be in this direction. T1x is going to be equal to what?
Cosine of 30.
Yeah, the cosine of 30 degrees times,
Times, is it times anything?
right?
Ah,
If you want to know T1x, you gotta use the angle, right, and then multiply by the actual tension in T1, right? Okay. T1y, or T1y is kind of the same deal, except we're going to be the sine of 30 degrees times T1, right? Now, we don't know what T1 is yet, but we can simplify these. It does make it into there. We can simplify these into 0.866 T1 and 0.5 T1. Okay. We can find the same thing for T2x, right? So let's say T2x is equal to what? Remember, we're saying this is 140 degrees. We've redefined it, right? The cosine of 140 times T2 is equal to, and that gets negative 0.76 T2. Because that's the cosine of 140. Somebody plug in the cosine of 40.
it's probably just positive 0.76.
Very good. It's just positive 0.76. Do we see why you can do it either way? They're both meaningful. In the end, you're going to wind up the same. This is where the math takes care of the direction for you, because you've used a consistent system. If you don't use the consistent system and you change where you're measuring your angle against, it's up to you, right, with your diagram and your carefulness to keep track of direction of forces.
Do you mean the consistent?
Do I what?
Is that-
The consistent.
Oh, consistent system. Consistent.
Consistent. The consistent, yes. Okay. So we're gonna run out of time. 0.62642. We call it 643. T2. All right. So we don't know what T1 and T2 are yet, but we know how their ratios are in terms of the vertical and horizontal, right? Okay, let's move on from there. So now he does what? Let's see how, I'm looking to see how he handles this. Finally, the weight vector must be split into its components. What is the weight equal to? According to equation 5.2, the weight is the mass times the acceleration due to gravity. The mass given is 5 kilograms. All right, we can actually write that down.
It's just
5 kilograms. So the force in newtons is 5 times 9.8, which is roughly 48 newtons. 48 newtons. Okay. Oh, sorry, he's got it in here. 49. What'd you say?
How does that?
Oh, you were
say
just whispering.
49?
all they're asking for that, or I guess for the components of it, is just the weight in the negative direction. Just gonna keep it consistent. So they split the vector up, but there's no reason to even split the vector up if you just.
Exactly. It's not meaningful. They spent time splitting the vector up, but it's not meaningful too. Because we know the vector is already straight down, right? Okay, so that's a trivial thing. So we know that this is 49 newtons. What do we know 49 newtons is equal to some unknowns summed together? What are those?
T1y plus T2.
Yeah, very good. The y components of both of these lines must equal our 49 newtons, right? So I'm going to say right here, 49 newtons equals T1y plus T2y. And we know that those happen to be equal to 0.5 T1, T1 plus 0.643 T2. That's T1. Okay. Trouble is, we don't know T1 and T2 yet. Do you see that? We got two unknowns.
So you have to.
So here's what we know. Ultimately, the y components of these two the y components of these two don't have to be equal. Okay? They just have to add up to.
Right. And they're not going to be equal because
So what do we know would be equal?
the
With the.
x, no, but the x components aren't equal.
Is anything cool?
The only thing that's equal is the y component going down is equal to the y components added together.
But the y components still are the same force. I guess the y components are.
This box, is it moving horizontally?
I thought we tied it off or whatever.
Is it moving horizontally?
No.
So what do we know about what's happening horizontally?
Oh, it's not moving at all. So the x
But
components
those
are
are equal then.
The x components have to be equal,
I
right?
thought we had tied it off, so I thought that we had said the x components don't always have to be equal if you
like
tie a knot or whatever.
No. We said the tension doesn't have to be equal. The components do have to be equal.
The
So
x
the knot
components
is
have to be
equal.
equal even if you tie a knot.
Well, because I guess.
The angles, right? It's going to move to an angle. Remember, think to our little problem where I said you start with a pot hanging right here and you tie a line to it, but you haven't pulled it yet. Okay? So there's basically zero tension on this line, right? So there's no force pulling it this way. Okay, now we put a little force on it, it starts to pull over. Okay? The y component of this tension line is a tiny little arrow, and it's pulling up a little bit on this, right? The y component of this one is pulling up. It's a pretty large arrow. The sum of these two has to equal the net weight of this thing pulling down, right? The x component of this line that's barely tipped over is pretty small, isn't it?
Yes.
Okay. And in order for this thing to not be accelerating in space, there has to be an equal and opposite force acting upon it. Otherwise, it's not going to be in static equilibrium, right? That opposite and equal force is the x component of this line. And this line, therefore, has a very low tension because I don't need a lot of counter tension here, right? This is not a big number because the angle is pretty small still. So this all comes out of the angles. It'll find its own happy place, and once it's still, you know that the forces acting in the x direction, they're equal. And you know the forces acting in the y direction, they're equal because it's not accelerating. Does that make sense? So we knew the forces in the y direction were this y, and gravity. So we summed those. Trouble was, we have too many unknowns. But in the x direction, we don't have too many unknowns. So here's what we do. We say in the x direction, what is the sum of the forces? Sum of the forces in the x direction is equal to what?
0.
0. Bingo. And then that's equal to t1x plus t2x. And that's equal to t1x is 0.866 t1. And what's t2?
Negative
t2x.
x.
Negative 0.76 t2. You see what we did there? Okay, so now we're just going to solve for t1. Because what we have to do, we have now two equations and two unknowns. You always need as many equations as unknowns you have. Okay? One equation, one unknown, you can solve it. Two equations, two unknowns, you can solve it. Okay. So let's just find out what t1 equals. We know that 0, actually, so we'll, I'm going to add this to both sides. Does that make sense? So I wind up with 0.76 t2 is equal to 0.8, one of my zeros been leaving 0, 0.866 t1. And now I'm just going to divide both sides. We'll just make t2 the one that we do. We get 0.866 over 0.76 t1. So that's the relationship between t2 and t1. Will somebody simplify that for me?
1.13.
1.13
T1.
t1. Good. Does that appear on our board? Yeah. Good. Are you guys following what we did so far? What do we do with this little fact that we just determined? That T2 equals that. What do we do with that fact?
Plug it in for T2 and
Yeah, we're going to plug it into our other equation. Good. So I'm going to take 1.13 T1, and where am I going to plug it in?
Into T2.
Yeah, that's what T2 is equal to, right? So I wish I had architected my problem differently, but it's okay. We can still make it work. We're going to plug this in right there. So we get this is equal to 0.5 T1 plus 0.643, and we just create a parenthesis and we plug in exactly what T2 is equal to, 1.13 T1. Okay, now I'm going to copy that problem up over here so that we have a little bit more space. We have 49 newtons is equal to 0.5 T1, right? Plus 0.643 times 1.13 T1. Right? So now let's just, what's 0.643 times 1.13?
They don't give it to us, which is unfortunate. 1.13 times 0.643. 0.73.
So 49 is equal to these together. Now let's get T1 by itself. First of all, we just need to combine what's, this is going to be 1.23, right?
Yes.
So that's equal to 1.23 T1. And now I'm just going to divide. So T1 has to be equal to 49 divided by 1.23 newtons, which is equal to
4. Roughly.
4.0
Oh, 4,
times
sorry.
10.
I was going to say, it's not.
It's 4.0 times 10 to the 1, which
Ah.
I don't know why you do that, because it's more
Because
characters.
those
but-
Because if you write 40 newtons, then it is only one significant figure, but if you write 4.0 times 10 to the 1, then it's
Yeah, I know, but it's dumb. Just write
You-
40.
It's scientific.
But if you
It's-
write 40.0, then you have 3 significant figures,
Right. Okay.
which is illegal.
Which is terrible.
You
Okay.
just write
So we've got 40 newtons. What about T2? What does T2 equal to?
I can plug it into the T1 equation.
Yeah, we're just going to plug it right into that, right? So tell me what 1.13 times 40 is.
45.
Okay, 1.13 times
Not 4.5 times 10 to the 1.
45 newtons. Okay, so here's what we did. We just determined that they have unequal tensions, right? We got 40 newtons over here, 45 newtons over here, and we have solved how much tension there is in each of these lines. Okay? Kind of a cool little problem. It becomes pretty important to think about the two problems that are embedded in every problem that is two-dimensional. There is a problem in the vertical dimension, and there's a problem in the horizontal dimension. Typically, there is information that interlinks the two, right? And one may be needed to solve the other. That's what we found here, right? We knew that when we added up the vertical, it had to be 49, but we had two unknowns. We knew that when we added up the horizontal, it had to be 0, and we had two unknowns. Solve for one, plug it into the other, bingo. Okay? All right, so that is a good start to chapter 6, and we're a little over time. You know your homework is that test, right? And I need you guys to turn in your homework that was due today.
Do you want to see my other stuff too?
I looked at it before. I gave everybody I gave you guys all basically full credit for the practice problems.
Oh, I guess I
For
have
review
it.
as practice problems. Because I checked them visually and I saw that you guys had put the time in.
Well, I mean, I was gone.
What's
Friday, so it was like,
Say that again. Sorry.
I was gone on Friday. So,
Oh, yes, you were. So I didn't see yours. Actually, you're right.
so this is 1 to 10 on questions.
Yep.
And all the way through.
Good job. Did you get a chance to watch that video? Did that work for you?
I didn't get to watch all of it. I'm going to finish that soon. So I will.
What?
I know. Yeah.
Okay. Exciting conclusions here. So we're about halfway through the year. We're gonna probably, as we finish the bend of this fall. Well, at the end of Christmas, right? And we've got Friday and what, one day next week?
We're not even gonna get halfway through this calculus book.
You know, that's for other times to think about.
Okay. Yeah. So here, I just want us to do a quick tiny look ahead. Okay. So we're gonna finish module 6. My hope is basically by Christmas, roughly. Although it's gonna stretch a tiny bit into January. Okay. Then we can just look ahead. Module 7, uniform circular motion. So that's things like planets going around, or me swinging a string, a weight at the end of a string, right? Things like problems like that. Then we're going to start. We sort of turn in a new direction, and we start talking about work and energy. Pretty interesting. Then I think we're going to have some choices, and I would encourage you guys, if you want to take a few minutes to look through, maybe over Christmas, modules 10 through 16, and identify the ones that you find that sound really interesting to you. Because we're not going to get through all the modules. They're not entirely interdependent. In other words, I don't think you have to have done 10 to do 11. It might help, but I don't think you have to. So maybe you guys would say, I'm really not that interested in optics, but I would really love to understand electric fields more, or vice versa. Okay? So I would over Christmas, I'm going to ask you guys to do a little thinking on that, so that we can kind of chart our course for the spring here and focus on things that you find kind of interesting and exciting. Okay? Let me know if you're having trouble with this. And Josiah, I don't know if you'll be able to do this by Friday or not. Probably not, because I don't know. We need to chat. So let me know.
He's not going to be here for the rest of school.
He's not going to be here for this week, which means he might not be here next week
He's
either.
not going to be here next week. All right.
Yeah.
So.
Okay. So the meaning of that is he and I are going to get to have some fun with each other over Christmas vacation. Da, da, da. All right.
He's gonna love that.
He will love it. He loves spending time with me on the phone, right? Okay. I'm going to stop it now.